The outer reaches of our solar system contain two fascinating yet distinctly different regions of primordial material, the Kuiper Belt and the Oort Cloud. Both structures represent critical reservoirs of ancient icy bodies that have remained relatively unchanged since the formation of our solar system approximately 4.6 billion years ago. These regions not only provide astronomers with valuable insights into the early solar system's composition and formation processes, but also serve as the source regions for comets that occasionally venture into the inner solar system. While they share some similarities as repositories of primordial material, the Kuiper Belt and Oort Cloud differ significantly in their location, structure, composition, and gravitational influences. This comprehensive analysis explores the key differences between these two outer solar system features, detailing their unique characteristics and scientific importance. The most fundamental difference between the Kuiper Belt and the Oort Cloud lies in their distance from the Sun and their spatial distribution within the solar system. The Kuiper Belt is relatively closer, beginning just beyond Neptune's orbit, at approximately 30 astronomical units, AU, from the Sun, and extending to about 55 AU. This region forms the first significant boundary beyond the major planets. Its main concentration extends from the 2-3 mean motion resonance with Neptune at 39.5 AU to the 1.2 resonance at roughly 48 AU, with what astronomers call the Kuiper Cliff, marking a significant drop-off in object density around 50 AU. In stark contrast, the Oort Cloud exists at vastly greater distances, beginning at approximately 2,000 AU from the Sun and extending outward to nearly 200,000 AU, roughly 3.2 light-years. This places its innermost region more than 1,000 times farther from the Sun than the Kuiper Belt. The Oort Cloud's extreme distance places it at the very edge of the Sun's gravitational influence, where the gravitational effects of passing stars and the Milky Way galaxy itself become significant factors. This remote region effectively marks the cosmographic boundary of our solar system, defining the outer limits of the Sun's dominion in space. The immense separation between these two regions highlights their distinct nature and formation histories within our solar system's architecture. The physical arrangements of the Kuiper Belt and Oort Cloud represent another significant area of difference between these outer solar system structures. The Kuiper Belt forms a relatively flat, disc-shaped region that generally aligns with the ecliptic plane of the solar system, though it is quite thick, extending as much as 10 degrees beyond the ecliptic, with a more diffuse distribution stretching several times farther. Despite being commonly referred to as a belt, its overall structure more closely resembles a torus or donut than a thin band, with its mean position inclined to the ecliptic by 1.86 degrees. This configuration reflects its evolution within the same orbital plane as the planets. The Oort Cloud, however, presents a fundamentally different shape. It encompasses two distinct regions: a disc-shaped inner Oort Cloud, sometimes called the Hills Cloud, that aligns with the solar ecliptic, and a much larger spherical outer Oort Cloud that completely envelops the solar system. This spherical distribution is particularly noteworthy as it contrasts sharply with the primarily flat arrangement of objects in the inner solar system, including the Kuiper Belt. The spherical configuration of the outer Oort Cloud suggests different formation processes and evolutionary history compared to the more planar Kuiper Belt, and it reflects the influence of external gravitational forces that have acted upon these distant objects over billions of years. The formation histories of the Kuiper Belt and Oort Cloud reveal important differences that have shaped their current configurations. Both regions contain primordial material from the solar system's early development, but they have experienced different evolutionary paths. The Oort Cloud is generally understood to be a direct residue of the original protoplanetary disk that formed around the Sun approximately 4.6 billion years ago. Many of its objects are believed to have formed closer to the Sun before being gravitationally scattered outward by the giant planets during the early chaotic period of solar system formation. The Kuiper Belt's origin appears more complex and remains somewhat unclear to astronomers. Computer simulations based on the NICE model of solar system evolution suggest that the Kuiper Belt we observe today may not be entirely in its original configuration. The model proposes that gravitational interactions with the giant planets, particularly Neptune, significantly reshape the Kuiper Belt, creating its current structure with distinct cold and hot populations of objects. The presence of various resonant objects and the scattered disk provides evidence of this dynamic history. However, some characteristics, such as the frequency of binary objects in the cold belt, suggest that portions of the Kuiper Belt may have formed at their current locations, representing the only truly local population of small bodies in the solar system. Both the Kuiper Belt and Oort Cloud contain icy bodies primarily composed of methane, water, and ammonia, reflecting their formation in the cold outer regions of the solar nebula. However, they host different types of notable objects. The Kuiper Belt contains several dwarf planets, with Pluto being its largest and most massive member. Originally classified as the 9th planet of our solar system, Pluto's reclassification as a dwarf planet in 2006 came partially due to the discovery of numerous similar objects in the Kuiper Belt, including Haumea and Makemake. The Kuiper Belt also contains a class of objects known as Plutinos that share Pluto's 2.3 resonant orbit with Neptune. The Oort Cloud, being much more distant and difficult to observe directly, has fewer individually identified objects. It is theorized to contain trillions of icy planetesimals, ranging from small comet nuclei to potentially larger bodies. While no large dwarf planets have been definitively identified within the Oort Cloud, astronomers believe it serves as the reservoir for long-period comets that occasionally get disturbed by passing stars and subsequently enter the inner solar system. The composition of these comets provides important clues about the nature of objects in the Oort Cloud, suggesting they retain some of the most pristine materials from the solar system's formation. The gravitational influences affecting objects in these two regions differ substantially, leading to distinct dynamic behaviors. The Kuiper Belt exists within the significant gravitational influence of Neptune, which creates a complex system of orbital resonances that shape the belt structure. These resonances create pronounced gaps in the Kuiper Belt's layout, similar to the Kirkwood gaps in the asteroid belt, and they stabilize the orbits of many Kuiper Belt objects. The region between 40 and 42 AU, for instance, contains no objects in stable orbits over long timescales due to Neptune's gravitational effects. The Oort Cloud, in contrast, exists at the boundary between solar and galactic gravitational dominion. Its constituents are only loosely bound to the solar system and are easily influenced by the gravitational pulls of passing stars and the Milky Way galaxy itself. These external forces have moderated the highly eccentric orbits of material ejected from the inner solar system, rendering them more circular through galactic gravitational torquing. Interestingly, these same galactic interferences occasionally dislodge comets from their orbits within the cloud, sending them toward the inner solar system as long-period comets. This fundamental difference in gravitational stability represents one of the most significant distinctions between the Kuiper Belt and Oort Cloud regions. Perhaps the most observationally significant difference between the Kuiper Belt and Oort Cloud lies in the types of comets they contribute to the inner solar system. The Kuiper Belt is the primary source of short-period or periodic comets, which have orbital periods of less than 200 years. The classic example is Halley's Comet, which returns to the inner solar system approximately every 76 years. These comets maintain relatively stable orbits that bring them repeatedly into the planetary region of the solar system. The Oort Cloud, on the other hand, serves as the source region for long-period comets, with orbital periods spanning thousands of years. Comets like Hale-Bopp, with its approximately 2,500-year orbital period, originated in the Oort Cloud. These long-period comets often appear unexpectedly from any direction in the sky, reflecting the spherical distribution of their source region, whereas short-period comets tend to approach from near the ecliptic plane, consistent with the disc-shaped Kuiper Belt. This distinction in cometary contributions provides astronomers with valuable observational evidence for the different structures and locations of these two regions. The Kuiper Belt and Oort Cloud represent two distinctly different regions in the outer solar system, each with unique characteristics that reflect their different formation histories and evolutionary paths. While both contain primordial material from the early solar system, they differ fundamentally in their distance from the Sun, physical structure, gravitational dynamics, and cometary contributions. The Kuiper Belt forms a relatively nearby, disc-shaped region strongly influenced by Neptune, while the Oort Cloud exists as a distant, primarily spherical structure at the boundary between solar and galactic influence. These differences not only help astronomers understand the complex architecture of our solar system, but also provide valuable insights into the processes that shaped its formation and evolution over the past 4.6 billion years. As observational technologies continue to improve, our understanding of these fascinating outer solar system regions will undoubtedly deepen, potentially revealing new differences and similarities between the Kuiper Belt and Oort Cloud.